Alright, hello and welcome back to Tomography. So, I thought it would be nice to get out a little bit. I've actually been locked in my house since like March-ish, and the only time I ever really go outside is to take out the trash. I've left the house like once, twice since then, and been outside in the sun only a handful of times. So I thought I'd try to enjoy my backyard for a few minutes while recording. I think this is actually the first time I've ever actually been here since I moved in like a year and a half ago. It's just everything's been super busy, and then the pandemic just put everybody in sort of a survival mode. So I guess it being Florida, I've been out here for all of like 10 minutes to set up the camera. I'm already sweating. So maybe I'll have to wait before I spend more time out here, and like a little bit further into winter. But yeah, welcome to my backyard. So what did we do last time? Let's see. So we talked about filters, and that's the beginning of signal processing. So we related the central slice theorem and the filtered back projection to a filtering on the radon transform. The filtering on the radon transform, being sort of absolute value S. But there was no Fourier transform, no function whose Fourier transform gives you absolute value of S, and so we then went to sort of these low-pass filters, like the Shep-Logan filter, that we used to replace the absolute value of S, and then the idea is that that should give us a better approximation. We want to use a low-pass filter in there as well, just because if we just use the absolute value of S, then we're going to be amplifying a lot of noise. And so these other low-pass filters are basically functions that vanish outside of a certain region, and so then therefore only lower frequencies survive. So that's the beginning of sort of the signal processing journey that we're about to take. The next one approaches a different practical problem, where basically the central slice theorem depends on us having perfect resolution of our or sort of the full continuum of samples. So it requires all of the angles and all of the T and etc. But as we've seen just playing around with MATLAB, we're not going to get that. We only have a few samples of the radon transform through our sinograms, and you can't put people through an uncountable number of X-rays and expect to get a result. So in this light, we are going to be taking a look at sampling theorems for signal processing and what is called the discrete Fourier transform. So the discrete Fourier transform will lead us to Fourier series, and then we can talk about things like sampling theorems, Nyquist sampling theorem, which is also known as the Shannon-Whittaker sampling theorem, and for band-limited functions. So we're going to start the lecture off with that, and I'm going to go through the sort of heuristic argument that you get out of Feynman's book, and then we'll go back and try to fill in the theoretical gaps in the light of our tempered distributions. So generally speaking, we're going to be talking about Fourier series, and then there's some question about convergence of Fourier series, and the Fourier transform of periodic function naturally leads to Fourier series, and we'll take a look at that where we view the Fourier transform of a periodic function through the lens of tempered distributions. I live next to a nature preserve, which is nice, I guess, but maybe not the best for recording. Okay. So that's where we're going to go ahead and start off, and I'll go back inside to actually record. But maybe I'll enjoy this for a few more minutes. I have flowers in my backyard. I had no clue. All right. See you on the other side. So thus far we've been talking about sort of the most important theorem that comes out of tomography, and that is the central slice theorem, which is what gives us a filtered back projection. So basically we have f of xy is equal to 1/2 of the back projection of the inverse Fourier transform acting on the absolute value of S, where S is a frequency, of the Fourier transform, the radon transform of F, of S theta. And again, this Fourier transform only is responsible for the first variable, so we leave theta fixed. And then after doing that back projection, then what we finally get is a function in xy. And so basically what we have is that we have a precise recovery of the function f. Unfortunately, we saw that for coming from data, one problem that we run into is that since we have noisy data, using just the absolute value of s is not practical because you're going to be amplifying noise quite a bit. And so then we talked about low-pass filters, and so basically we took a low-pass filter which is of the form something like the absolute value of s times the square wave of some width of s, and then times some big function of s in some way. And then sometimes we wanted this f would make everything continuous, other times it would just be sort of we just end up with a hard cutoff at L. There's a lot of different things that would end up happening. There was a Shep-Logan the Shep-Logan filter, etc. But if we call this A of S, then what we replace the absolute value of S with is A, and what ultimately that gives us is the back projection acting on the convolution of the inverse of A convolved with the radon transform of F, right? And so this simplifies a lot of things. Of course, you're still left with trying to figure out what this is, but we can get back to that later. Okay, so there's another practical problem that we end up running into, and so this, it's you sort of treating noise here, and so then so that we use the low-pass filters, but now we're dealing with another one, and it's called sampling. We don't have the whole radon transform. So generally speaking, what we have is we have this. We have a whole collection of pixels, and so we don't have a continuous the continuous thing we would like to believe we do up here, and we can only take a certain number of angles. In this light, we are actually going to have to start talking about how do we get, basically how far away are we if we only use these discrete samples of the radon transform. And so that's going to be the subject of today's lecture. So this comes down to sampling. And so generally speaking, we're going to be talking about a function f, and we're going to be talking about samples that come from it. So if you look at my numerical analysis class, actually, we talk a good deal about recovering functions from samples using the Bernstein polynomial approximation, interpolation, and etc. And those are all excellent ways of getting an approximation of a function. However, this method that we're going to be talking about today is more tuned at recovering a function from its sort of frequency elements. And so we're going to be developing what is called the Fourier series. So we'll build up to that one bit at a time, and eventually what we're going to do is going to be called Fourier Interpolation. So let's go ahead and get started. So basically, the idea is that we have a finite number of samples of a function. So some function f, 1, 2, 3, 4, 5, 6, 7, some finite number of samples, and so this is all we really know about f. And so there's questions of when can we recover f from a discrete set of samples. right? And that is a sort of central question of approximation theory. And it turns out if the Fourier transform of f is 0 outside a region, just sort of like what we were talking about before with low-pass filters, and we call these functions band limited, then a certain density of points allows us to recover the entire function. And this is going to be called, say, the Shannon-Whittaker. I can't remember how to spell his name exactly, but theorem, or sometimes the Nyquist sampling theorem. And so when I say a certain density, what I'm talking about is a certain frequency of samples. So and that'll be directly related to the sort of the support of the Fourier transform where it's not 0. So that's where we're going to be talking about today. Okay, so what I'm going to do is I'm just going to go through this sort of heuristic argument that Timothy Feeman does in his textbook, and here we're in chapter 8, and then we'll follow it up with some more precise language that fits the theory that we've been developing with the Schwartz space and temperature distributions, just to put it on solid ground. And so to start, we're going to suppose f is a function with a Fourier transform, and so it's going to be f of f that vanishes outside of or say vanishes for absolute value of the frequency bigger than L. Okay. And so we're going to start off with a definition, and this is the Fourier series coefficient. The Fourier series coefficient of f, the Fourier transform of f, is given as this. And so it's going to be, say, Cn is equal to 1 over 2L times the integral from minus L to L of the Fourier transform of f evaluated at omega times e to the minus I pi n omega divided by L. And this is integral d omega. So it's clear that if we even change this from being negative L to L to negative infinity to infinity, that in this particular case that we care about, this is going to be 0. And so we're also assuming in this definition that we were talking about this guy. So L is not just arbitrary in this definition, but we're talking about a function that vanishes for w outside of L. We could, of course, just put negative infinity to infinity here, and it wouldn't actually change anything about this definition in this case. Okay, so then if we go ahead and take a look at a function, so we have 2 pi times f of pi n over L, following Feeman. So basically what we're going to do is we're going to replace f with the Fourier transform and then the inverse Fourier transform hit against it. So it's going to be f inverse the Fourier transform of f
at pi n over L, and that's fairly reasonable. So assuming that f can be recovered from its inverse Fourier transform, so in this case something like function in Schwartz space, then this is a perfectly valid operation. So then we take the integral from negative infinity to infinity of f. So just expand this definition of the inverse. We get this, e to the I pi omega pi over pi n over L d omega. And then of course, like I just said, this is has no bearing here of this integral. So integral from negative L to L, the Fourier transform of f omega e to the I omega pi n over L and d omega. Let's see. And yeah. So ultimately, this gives me 2L times C of minus n by definition. So I was sort of flying loose here with this definition. Here we might actually end up needing a 2 pi or square root of 2 pi here. I think actually we do need that. 1 over square root of 2 pi. Just the difference between Feynman's definition and what we had in applied analysis. But overall, the combination of f inverse and f will give us the 2 pi as a whole here, one way or the other. So yeah, ultimately we end up with this no matter what definition of Fourier transform we used. Okay, so yeah, so then that tells us this, that C of minus n is equal to pi over L times f of pi n over L for all integers n. Okay. So then he uses some results from Fourier series, which we'll talk about in a minute. But basically what he says then is this. We have the Fourier transform of f at omega is equal to the sum n equals negative infinity to infinity of c minus n e to the minus I n pi omega divided by L is equal to pi over L times, and this is just using the Cn definition, n equals negative infinity to infinity of f of pi n divided by L times e to the minus I n pi omega divided by L. And there we go. So basically, at the end of the day, what we see is that we are achieving the Fourier transform of f just from samples of the function itself. And then we can take this a little bit further, and we can take a look at, so now we're still trying to get f of x. And so this is going to be giving us, we're going to apply the inverse Fourier transform to the Fourier transform of f. And we're looking at this at x. So then what we're going to do is just apply that formula we just made up, but put it in here, 1 over, say, square root of 2 pi by the symmetric definition, is the integral from negative L to L of f of the Fourier transform of f at omega e to the I omega x. And now we can plug in that this guy that we just found here. So when we do that, what are we going to get? We're going to get 1 over, say, square root of 2 pi times the integral from minus L to L. We're going to have pi over L popping out. And then on the inside, we have the sum n equals negative infinity to infinity of f of pi n over L times e to the minus I n pi omega over L times e to the I omega x dx. Okay, so just plugging that in. And let me see, just double checking some coefficients here. Yeah, so like I said before, we actually need this 1 over 2 pi square root here. So we're going to put square root of 2 pi at the bottom. And yeah, just double checking. That's it, right? I think that's all I'm missing. Anyway, because the reason why I'm saying that is because we're definitely going to need this guy squared here. Let's see. Okay. Yep. All right. Keeping moving. And so I think that's also gonna. Yeah. Okay. I'm gonna stop. Sorry. It gives me a headache keeping track of these coefficients. I think Feynman just declares that 2 pi is equal to 1 in his work, just to avoid having to worry about these coefficients. But of course, mathematically, you have to keep track of these if you want to get precise formulas. But at worst, you're only ever off by like 2 pi or square root of 2 pi or something like that. Okay, so keep it moving. So we have square root of 2 pi on the bottom here, and then we have pi on the top. So that's just going to cancel to be pi over 2, 1/2. And so that leaves us 1 over 2L here. And then we're going to have the sum n equals 0, negative infinity to infinity, moving the integral to the inside. And what we're going to be left with is this, f of pi n divided by L, times the integral from minus L to L of e to the I omega Lx minus n pi divided by L dw. And yeah, so continuing on with this, we can actually go ahead and see that we get this 1 over 2L times the sum n equals negative infinity to infinity. So that f term sticks in here, pi n over L. We're going to have a 2L term come out. And then we've done this integral before, so I'm just going to go ahead and put it in here. So it's going to be the sine of Lx minus n pi divided by Lx minus n pi. And yeah, so then we can just finally wrap this up and cancel 2L with 2L. And we get the sum n equals negative infinity to infinity of f of pi n divided by L times sine of Lx minus n pi divided by Lx minus n pi. Okay, so looking through here, we basically previously we developed a Fourier series for a band-limited function, and so we ended up getting this. And then after that, we just played through and replaced that definition here and just followed our nose. Should have had this dx up here. And so basically, if you just take this Fourier transform and expand it on the inside, ultimately, what you're led down to is this integral. This integral we did back when we were talking about delta sequences. And we saw that it gives us the sinc function, which is this. So interesting thing about sinc function is it is at 1 at 0. And so we see that if I put in here for x, if instead of x I put in pi n over L, I get, for that particular term for n, I get just pi n, so it becomes pi n minus pi n, and so sine will be 0. But then we have it divided by 0 on the bottom, but because sine is 0 at 0, and basically those terms cancel, and it gives you 1. And then for all the other terms, where m is not equal to n, we're going to get basically sine of some integer times pi, where that integer is not 0. And so then sine is 0 there. And so we can see that this interpolates f at x equals pi n over L. So it agrees exactly with f at each of these points, and then it does whatever it does on the inside. But we have, not only is it interpolating, it is actually exactly equal to, and so that's really handy. And so we see that if we have a band-limited function, then if we sample at the function at these particular points, then, and that is L here, then we get exact reconstruction, and this is the Nyquist frequency, if you want. So pi over L. And so the Nyquist theorem basically says if you have a band-limited function, then you exactly reproduce your function f with just these samples. So it's not just an approximation method, but it's an exact reconstruction method. And that's really handy because f is, we can only sample f at a finite number of places. So this does require that your function is band-limited. And so the examples of band-limited functions would be, sine and cosine, etc. Things that aren't band-limited would be, say, the Gaussian. It decays really fast, and so you'd probably be good with an approximation, assuming that it is band-limited for some big L. But it isn't technically, so then in that case, we'd end up getting just an approximation. But if you take sine, cosine, or some trigonometric sum, so just like a whole bunch of collection of frequencies of sines and cosines and add them together, as long as it's finite, you win. And yeah, so that's nice. But in order to justify this, theoretically, we really should go through and do a little bit more of a discussion about these things. But before we run off and do that, let's just state Nyquist theorem. So, of course, my pencil dies. Okay, so here we're going to be following applied analysis again, and this is going to be chapter 7 that we start in. So chapter 11 in the book covers the Fourier transform, but chapter 7 includes information on wavelet transforms and a few other things. And in particular, it also talks about Fourier series. So I'm going to go ahead and do some definitions to get us started. So we already had the definition of Cn. But here we're going to be assuming, for the duration, we assume that f is a periodic function over the interval 0 to 2 pi. Now, before we were assuming it was a periodic function of period, say, 2L, more or less. Well, that's where we applied it in the situation. And we can take all these methods and sort of rescale them to make it fit. And so in this case, we're defining Cn as, and also sometimes we'll refer to it as f hat of n as 1 over the square root of 2 pi times the integral from 0 to 2 pi of f of x times e to the minus I n x dx. So in this case, we're just going to be integrating over one period and multiplying by e to the minus I n x, where n is an integer. So n is no longer living in space of real numbers when you talk about periodic functions, and that's partly because of what we just talked about with the Nyquist frequency. You can get exact reproduction of periodic functions using only a countable number of these terms, a countable number of coefficients. So and so we'll see how we can get from the Fourier transform back to this exactly, and that's going to come through the Poisson summation formula, which we'll prove later. Okay, so let's go ahead and get started with this. What we're trying to do is we're trying to prove lemma is 7.8, and we'll prove it in a little bit more less generality than what they're doing, because they're doing this with general Sobolev spaces, and they need those theorems for PDEs. But for us, we just need it to be continuously differentiable, and so we only need one derivative, and so that should be enough. So let's go ahead and start. So we have a lemma 7.8. And so we're going to suppose that f is c1 of 0 to 2 pi, so continuously differentiable. And then we're going to let Sn be the partial sum of what we're going to call as our Fourier series. So 1 over square root of 2 pi times the sum n equals negative n to n. So it's a symmetric partial sum of fn hat e to the I n x. And so this is a lot like our inverse Fourier transform that we were dealing with before. But instead of an integral, we were just doing a sum, and this sort of lines up with what we're talking about with the difference between the continuum of points versus this countable number one. So let's see. So this is the nth partial sum of the Fourier series of f. So the Fourier series is what you get when you take n goes to infinity. And we're going to define this quantity, the magnitude of f prime, is equal to the sum n equals negative infinity to infinity of n to the n squared times f hat of n squared to the 1/2. So basically we're taking a look at the norm of these coefficients in the L2 sense. So what you can see immediately, let's finish out the definition and then I'll talk about that. Then there exists constant c greater than 0 independent of f, such that we get this. Sn minus f at infinity is less or equal to, say, c over n to the negative 1/2 of f prime. 1 minus 1/2. So just that's what happens when you try to specialize on the spot. So this is actually a rather slow convergence, but if you increase the order of derivatives, you can increase the magnitude at which this grows. So if you have a really, really smooth function, this should converge really, really fast. So do I want to go? Why don't we just go ahead and do that then? Let's put ck up here, and then what you're going to get is 2k here, and then put a kth derivative here, and at the end of the day, we end up getting nk minus 1/2, and so times this. And so generally the idea is that as k goes to infinity, as for really highly smooth functions, the decay rate of the terms of the Fourier series is very high, and so basically that means that your Fourier series is going to converge much, much faster. So let's go ahead and cancel this out, and so now let's go ahead and take a look. So one thing to note, and where a lot of this is coming from, is this. So if you take a look, proof. And so the first thing to do is to note that if f hat of n is equal to the sum of 1 over square root of 2 pi times, 1 over square root of 2 pi times the integral from 0 to 2 pi of f of x times e to the minus I n x dx. Then as we keep applying derivatives, and this is just the same thing that we saw with the Fourier transform, that we end up getting, we pop out n terms. So basically what we end up having is this the Fourier coefficient of fk at n is going to give us in to the k of f and k, right? And so you can see that's where this sort of extra term is going to be coming out of. So let's group that up here. And so that's the idea that we're going to be using in order to get this bound on the error of the difference between the Fourier series, the partial sum, and the function itself. Okay, so let's start. So this is just following the book Applied Analysis, like I said before. So since Sn is in C of t for every n, and I mean that's pretty obvious. These are just exponential functions, and if there's a finite number of them, then yeah, they're C infinity of and not t. That's of 0 to pi. Then it's sufficient to show that the sequence Sn is Koshi within, say, C 0 to pi with respect to the supremum norm, or the uniform norm. Right, so we want to show that, basically we want to show this. For all n and m, with, say, m bigger than n, we have Sn minus Sm is less than or equal to sum over a square root of 2 pi, less than or equal to c over nk minus 1/2 of fk. And here I'm taking this as the infinity norm here. So this is the uniform norm, the supremum for of Sn minus Sm over 0 to pi. And so once we establish this, basically what we can see is that for large enough n, this difference is going to be less than epsilon, when this term drags it underneath epsilon. And so then that will give us that as Koshi, and therefore since the collection of continuous functions over a compact interval is complete, that means they must be converging to something, and well, we call that something the Fourier series. So then going through these calculations is what we get. We have Sn minus Sm uniform norm. Well, this is what it is going to be the sum of n. Let's see, n less than or equal to the absolute value of n less than or equal to m. So we're just carving out. So we have a whole bunch of points in the series, and it's symmetric about 0. So this is m, this is minus m, and so then we're saying, all right, we're going to chop out these middle terms here from this bit, and so all that's left is going to be these guys here. And so that's what gives you this term. And let's see. So for that, what's left over is we end up having the norm of fn hat e to the, just looking at the definition of s, we have inx here. So I'm going to put that there, e to the inx. And then we have a 1 over square root of 2 pi. Right? But I can crash through the absolute values by the triangle inequality, and that gives me 1 over square root of 2 pi times the sum of n less than capital N less than or equal to m of the absolute value of the Fourier series coefficient, and that other term, well, this is always bounded by 1, so I can just leave that alone. Okay. Now, if I multiply and divide by the absolute value of nk, then what do I get? So I get 1 over square root of 2 pi times the sum n less than absolute value of n less than m. So we're going to have n absolute value of k, fn hat, times 1 over the absolute value of nk. And we know that this is, just like I said before, going to be related to this. So that gives me this. This is equal to 1 over square root of 2 pi times the sum capital N less than or equal to, or less than absolute value of n less than or equal to m. And we're left with fk hat sub n times 1 over nk. Okay. Now, what we're going to use next is the Cauchy-Schwartz inequality. And so I'm going to take, if you remember Cauchy-Schwartz, let's go ahead and put it in red here. Gives us this. So the sum of an bn is less than or equal to, and say absolute values, the square root of the sum of an squared times the square root of the sum bn absolute value squared. Right? And so, employing this, what do we find? Is we have this inequality. We get that term on the last page is less than or equal to 1 over square root of 2 pi times, big brackets, the sum of n less than absolute value of n less than or equal to m. And here we have our term of f n k hat squared. Then we take square root, and then we have the sum of n less than absolute value less than or equal to m of these guys. 1 over absolute value of n to the 2k to the 1/2. Right? So, moving forward, what do we have? So, to start off, this is exactly what we talked about before. Square root of 2 pi. This is the norm of fk. And then this other term, we can bound it from above by this. So capital N to infinity of dr over r to 2k. And this comes straight from just calculus 2, where we have a decreasing sequence, and so we can upper bound it by an integrable function. And yeah. And so then when you work out all the arithmetic here, that's going to give you this. You get 1 over square root of 2 pi times 2k minus 1. This is again just doing a little bit of calculus 2. Times fk times 1 over n to the k minus 1/2. There we go. And so then this gives us our constant, and yeah, that proves the result. So we have thus we have for a, what we really cared about was for a periodic function f, we have this f of x is equal to the sum n equals n equals negative infinity up to infinity, 1 over of f hat of n times e to the I n x, and that is exact. Right. So for a periodic function that is, say, at least continuously differentiable, we have this Fourier series converges. Okay. So it's a nice result, and we see that if we increase the differentiability of f, then we get faster convergence of the series. But we have convergence, and that's where we start. Okay, so now I'd like to be able to connect the Fourier series with the Fourier transform. And in order to do that, we need to prove the Poisson summation formula. And in this case, we can see even though periodic functions don't necessarily have a well-defined integral for the Fourier transform, we can view them as symbols of regular temper distributions, and we know that those indeed have Fourier transforms. And so even if I write the integral and it looks like it shouldn't converge, generally speaking, it'll converge in the sense of temper distributions. The connection of the Fourier transform with Fourier series, we need to go through the what is called the Poisson summation formula. And with this one, basically, it says this. It's the sum for n equals negative infinity to infinity of f of 2 pi n is equal to 1 over the square root of 2 pi times the sum n equals negative infinity to infinity of f hat of n. So there is a connection then between the sum of the coefficients of f and its and the Fourier transform evaluated at integer points. And so this is the proper Fourier transform, not the Fourier coefficients. But we'll see that these are connected later. But one thing to notice is that this here on the left is actually a tempered distribution on f, provided just because if f is a Schwartz-based function, then it is rapidly decreasing, so the sum will always converge. And so so this is the tempered distribution that comes from the sum of these delta functions of 2 pi n. All right, so or if you'd like, they're at say x minus 2 pi n. N equals negative infinity to infinity, and it's called the Dirac comb. And yeah, so so in general, what we're going to use is we're going to use the Poisson summation formula to first of all is to really justify the convergence of things like this. And so whenever we see one side converging, then the other one's going to converge, and this sum converges not in the literal sense, because pointwise, I mean, these aren't functions, but it converges in the space of tempered distributions. So so in order to prove the Poisson summation formula, we need to prove the following theorem. And so in applied analysis, this is listed as the theorem 11.45, and says to suppose that f is a C1 function over R. And so if we have a Schwartz-based function, it certainly is. And there exists constants. And so we're going to have, say, a c bigger than 0, an epsilon bigger than 0, such that we have 1 plus x squared raised to the 1/2 plus epsilon times f of x is less than c, and then we're also going to have the absolute value of 1 plus x squared to the 1/2 plus epsilon f prime of x is less than c. And so basically what this really gives us is it tells us that the sum is actually going to converge because when we divide by this, it's basically going to satisfy the power rule for a series. And so so then we can just go ahead and declare the existence of that derivative. And then we want this guy to satisfy that same sort of quantity because ideally we would also like we're going to make a function that is going to be continuously differentiable, so we want the sum to still converge in that case. So then we have the following identity. So this is actually more general than the Poisson summation formula. N equals negative infinity to infinity of f of x plus 2 pi n is equal to 1 over the square root of 2 pi times the sum n equals negative infinity to infinity of e to the I n x f hat of n. So the Fourier transform n. And so you can see that you can get back to the Poisson summation formula by setting x equals 0. And because then this will go away and this becomes 1, right? So so this result is strictly stronger than what we actually want. Okay, so then let's go ahead and take a look at the proof. So we're going to go ahead and talk about this function g of x, which is equal to sum n equals minus infinity to infinity of f of x plus 2 pi n. All right, so we know that this function, that this sum converges, and we know that actually the derivative converges as well. And so therefore we can say that g is continuously differentiable. And by what we showed earlier, and I should also say g is 2 pi periodic. And so therefore we have this. We have that g of x is equal to the sum n equals negative infinity to infinity of 1 over 2 pi of integral from 0 to 2 pi of e to the minus I n y g of y dy times e to the I n x. And so we know that converges in fact uniformly on for x between 0 and 2 pi. So that's where the theorem stops, but it kind of leaves a lot up to the reader here. So so what we can do is we can actually go ahead and expand out what g is, and that'll give us a little bit more intuition on what's going on here. So we have the integral, so we have the 1 over 2 pi times the sum n equals negative infinity to infinity of the integral from 0 to 2 pi e to the minus I n y, and then inside here we have the sum. I'm going to use the index m now for the sum, negative infinity to infinity, and this is going to be f of x plus 2 pi m, and this is done dy, and then you have e to the I n x. Now, if I go ahead and take a look at this, I get sum 1 over 2 pi, and I exchange the integral and the summation here, and we can do this because these series are absolutely convergent, and the convergence is uniform. So so then we still have the sum n equals negative infinity to infinity out here, and on the inside we have the sum m equals negative infinity to infinity of e to the, well, here I'll just write e to the trying to figure out where to put this. All right, so we're going to have the integral from 0 to 2 pi of f of x plus 2 pi m times e to the minus I n y dy, and then e to the I n x. Now, if I replace y with y plus 2 pi m, then and that should have been y on the inside here, sorry, y right there. Then nothing actually ends up changing, and so then that means I can take a look at this and I can turn this, use just shifting and recombine all these sums, and this becomes 1 over 2 pi times sum n equals negative infinity to infinity of the integral from negative infinity to infinity of f of say f of y e to the minus I n y dy times e to the I n x. And if I take one of these guys and I put it in here, then this is the sum n equals negative infinity to infinity 1 over square root of 2 pi of f hat of n times e to the I n x, right? And on the other side, g was just the sum. And so then that is the proof. So now I have just demonstrated that basically that this is true, and then by setting x equals 0, you get that back. So so it's fairly handy. And so at the end of the day, we've just shown that the Dirac comb, we already know that the Dirac comb converges, but then we know that it's Fourier transform. That the related to Fourier transform converges, and in particular, what we can do is we can write out the Poisson summation formula like this, and so we get 1 over square root of 2 pi times the sum n equals negative infinity to infinity of f hat of n is equal to 1 over 2 pi times the sum n equals negative infinity to infinity times the integral of e to the minus I n x f of x dx. And so since this is basically a sum of tempered distributions with regular tempered distributions with t e to the minus I n x, and so that is what this tempered distribution looks like, I basically get this. So we know that in the Schwartz space sense, that this guy converges, the Dirac comb, 2 pi at x. That's just notation for it shifted around. N equals negative infinity to infinity. And on the right hand side, we're getting 1 over 2 pi times the sum n equals negative infinity to infinity of e to the I n x when we replace n with minus n. So that's pretty cool. And something that we should take away from this is that this doesn't actually converge pointwise as a function, as a series of functions, and that's because these all have norm 1 on the inside. So if you remember back from, say, calculus 2, infinite series only converges if the terms go to 0. And so this doesn't converge literally in the series sense, but it does converge in the sense of tempered distributions. So that's an important distinction, and now this is going to allow us to talk about the Fourier transform of periodic functions. Okay, so to wrap up, basically what we can see is that we're going to take a look at periodic functions as tempered distributions. And so what we're thinking, just to start, is that we're going to let f be a continuously differentiable function that has period 2 pi, and then if you take a look at its the regular tempered distribution inside Schwartz space, it has this property where basically if you do a shifting, tau 2 pi of tf is exactly just tf back, right? And so more generally, we can have we say that a tempered distribution is periodic with period 2 pi if tau of 2 pi t is equal to t. Okay, so in that case, you can do some work and you can show that the Fourier transform of t is 1 over square root of 2 pi times the sum from n equals -infinity to infinity of some coefficients tn of delta 2 pi n. And for Fourier coefficients, tn hat, they're complex. And so more than that, it turns out and this is just again following the applied analysis book discussion, that these have polynomial growth, which means that there is some c for which 1 plus n squared to the d over 2 bounds these coefficients, and hence it is a S star. Hence, sorry, I just had lunch and I keep taking breaks between going this, and so sometimes it's hard for me to jump back into it. But basically, this gives a hence the Fourier transform is a S star convergent series of delta functions. Okay. So then what you can do is you can use that pairing. It basically gives you t of x is equal to 1 over square root of 2 pi of sum n equals -infinity to infinity of t n hat e to the I n x. So if, since basically it is a sum of delta functions, the Fourier transform itself, if you want to invert it back, then we know that there is a relationship between the delta functions and e to the I n x. So there. And there you go. So for a periodic function, we can express it as its Fourier series, its Fourier transform as these delta functions, and those delta functions can then be used to show that you can recover your function with only the integer frequencies. So that is really handy. And so usually when we're talking about the tempered distributions and all this other stuff of like periodic functions, I mean, we just replace t with like sine of x, and then we go ahead and express it out like this. Okay, and in particular, if we just take a look at sine of x, I mean, this is fairly trivial. We have e to the I x minus e to the minus I x divided by 2i. And so hence we get 1 over 2i times e to the minus ix, negative there, plus 1 over 2i times e to the ix. and here we have explicitly the Fourier series of sine, and that's just comes from Euler's formula. And so basically, sometimes we call these trigonometric series when we, instead of just writing them as ETI and X, we can write them as sine and cosine, and yeah. Okay, so I covered, I think, everything I wanted to cover today, and so we can tie this back in. So if we now can talk about Fourier transforms of periodic functions, and we see that we even have an example of a band-limited function here. This band-limited function basically is Fourier transform, doesn't exist, is zero rather, outside of -1 and 1. And so ta-da, there's your example of a band-limited function. Because when you take the Fourier transform itself, it's going to give you delta of 2 pi n minus and delta 2 pi n, right? So it's just going to be 2 spikes. Yeah, there, like that. So sine hat of x is basically this, and so the Fourier transform of sine hat is basically well, the second one actually should be going down. It's basically that. And so then this is a band limited function, and outside here it's 0 and 0. And so generally speaking, any band limited function we can reproduce, and that goes back to what we're talking about back here with the Nyquist theorem. Here, so basically, if we start with a band limited function f, we can go through this whole spiel, and we needed this sort of Fourier transform of periodic functions ideas in order to get at this sort of idea. Anyway, I don't know. I think right now I'm just talking nonsense, and my brain's kind of fuzzed out. So I think I'll stop here, and we've shown everything I wanted to show today. So I'm going to cut back, and we'll see my backyard again.
Okay, so that was Shannon sampling theorem, band-limited functions, Fourier series, etc. And a lot of this we saw through Feynman's book in a few minutes, and but then we went on and we did a little bit more of a rigorous take on it. And here we use the applied analysis book. Okay. I think I'm going to go ahead and go back inside, and yeah, thank you for hanging in there with me.